Now I'm going to do another version of the draining problem. I'm first going to run the actual experiment. I'm going to have a cup here, and I will measure the upper diameter, the lower diameter. So the cup is of varying diameters, okay? So it's about 8.5 centimeters. I'm going to do a ballpark measurement here. 8.5 centimeters. The lower diameter of the cup is going to be 6.5 centimeters. Okay, and then the height of the cup, about 17.5 centimeters is the height. 17.5 centimeters. So what I'm going to do when we're ready to go is I'm going to fill this up completely with water. Then I'm going to poke a hole at the bottom, and now I have to measure the diameter of that hole. And then I'm going to time how long it takes to drain the water from the cup. Then we're going to go over to the board and actually solve this problem. It's a good physics problem illustrating a draining problem from an object that is with non-constant radius. So it's basically getting, the radius is getting smaller as you're going down, so it's funneling. You can do similar problems with this, like draining a bowl of soup, draining any other kind of shape, changing radius, okay? So now let's measure the diameter of the hole that I'm gonna poke in there. Okay, I'm gonna use this screwdriver, this portion of the screwdriver to poke the hole. So I'm gonna measure the diameter of it now and record it. The diameter is 3 millimeters. So let's record that. Okay, now I'm going to fill it up with water and we're set to go. Okay. So I'm going to do my best to start the stopwatch right when I poke the hole so that there's no gap in time, and then we'll measure how long it takes to drain this whole cup, and then we'll go over to the board and we'll actually solve the problem. Okay? So we'll poke the hole at the bottom here, and then start the stopwatch. And then time it. Right now it's 10 seconds. Okay, we are near the end right now. It's been 4 minutes. The rate of dripping has slowed down quite a bit. And we are almost done. A little bit left. 4 minutes, 20 seconds. 4 minutes, 40 seconds approximately, okay? So then we're going to do the calculations for this. 4 minutes, 40 seconds. So now we're going to do the actual problem that we did, that I showed you the experiment of. We filled a cup of water. The top diameter was 8.5. The bottom was 6.5. The height was 7.5. I poked the hole, diameter 3 millimeters, and then it took about 4 minutes and 40 seconds for me to drain that. I'm going to model this based on the draining a pool problem that I did recently. So I would like you to first watch that if you haven't seen it. Then we can, then you can watch this video, because this one is a little bit tougher to do. The diameter of the cup is constantly changing. So what we're going to do is put the XY axis here at the center. Okay. What we're going to do is come up for an equation that describes, see, if this is the Y axis, this behaves like a y equals y minus y1 is equal to m times x minus x1. So it describes, we want to come up with an equation that describes this line, right? Y minus, so the coordinates of this point are what? So this is the radius of the cup, so it's going to be half of this. So if the diameter is 6.5 centimeter, the radius is what? 3.25 centimeters, right? So we convert that to meters, we get what? 0.0325 meters. That's the radius of the bottom. 0.0325 meters. So the coordinates of that point is 0.0325, 0. The y coordinate is 0. And then the coordinates of this point would be half of that, 0.0. Then half of that is 425. And what? What's the vertical? It's the height of the column, right? So it's from here to here. So it's 0.175 meters. So go over 2 spaces. So now y minus y1, I can choose 0, is equal to the slope, which is rise over run, right? This one minus this one over this one minus this one, 0.0325. Okay, x minus, and then x1 I have to choose this one since I chose y1 as this one, right? 0.0325. So I'm going to cancel this, I'm going to cancel this, I'm going to get y is equal to what? Then I'm going to calculate what this is. Okay? Then of course I can multiply this in. What is my eventual goal? Well, my goal is to come up for an equation. If the column of water is at a certain elevation, I want to come up for an equation that describes the radius of the water at the top. See, what is the radius? It's actually the x value, right? As the water is draining, the radius of the column of water is getting less and less, and the radius is equal to the x value. So I want to come up for an equation that describes what the radius is as a function of the y, as a function of the elevation. So I'm going to take the 17, bring it here, y as a function of y. Okay? And that's equal to the radius as a function of y. Okay? Now I can apply the continuity equation. We can say A1 V1, the area of this, times the velocity with which it's going down, okay, is equal to the area of this one, A2, which is given by the diameter of the hole, times V2, right? So area is pi times what? This x squared, right? Let's just write it as pi x squared for now, V2, okay? So since this is the diameter, I'm doing diameter squared, and then I'm dividing it by 4. And then this is going to be, convert to meters, 123.003. So now pi cancels pi. And what do we get here? There. Okay, let's write this equation on the side because we're eventually going to need it. We're going to have x is equal to y over 17.5 plus 0.0325. Okay, so let's erase this. So now I have the pressure at the top plus rho g y1 2 squared. This part is very similar to the pool draining problem that we did. We're going to assume this pressure and this pressure is the same. This one is 0. The density cancels. The density cancels. Then I have g y1 is just the elevation of the water plus half v1 squared. Over here, half v2 squared, right? So wherever there's v2, I'm going to substitute this equation. v2 is going to be 4x squared over 0.003 squared v1 quantity squared. Okay? So I have to take v2, but then I have to square it again. So there's a bunch of squares going on over here, right? Well, we can multiply everything by 2, put the 2 over here, squared, right? Now what are we going to do? We're going to take the square root of both sides, square root, square root, square root. This is similar to the pool draining equation that we did, right? Then what are we going to get here? Let's write y dt. Now I take the dt to the other side, I bring the radical 2gy down here, and then we're going to get this big equation. Okay? Our goal now is to try to simplify this as much as possible, and then it's eventually going to be put into the TI so that the TI can integrate this. Let's see here, we're going to do, we could put this under the same radical since they're both radical, of course. 1.975 times 10 to the 11th x to the fourth minus 1 over 19.6y dy. X, now I'm going to use this equation. So you have this number came from this, and then the x I substituted, then I raised it to the power of 4 minus 1 over, this is 19.6 came from 2g, and then y. And then we can integrate this, and then here, of course, we're just going to get t, right? The time that it takes to drain. Remember, the height was 17.5 centimeters, right? So it's 0.175 meters. So the original height was 0.175 meters, 0.175 to 0. And then the negative switches the order of the integral, so you get 0 to 0.175. So take this and put it into the TI and have the TI calculate the integral. And when you're done calculating the integral, it will already give you the time, okay? So let's put this in. Okay, the integral comes out to be 108.59 seconds. So that means 1 minute 48 seconds. Well, that's interesting. When we ran it, we actually got 4 minutes 40 seconds. And this equation and everything we predicted that it should drain in 1 minute 48 seconds, maybe at most 2 minutes, right? So when this kind of stuff happens, what you do is you go back through all your calculations, see if you went anywhere wrong. Then you go back to your measurements and start measuring them. I might have measured some things wrong. You measure the diameter again, you measure the inner diameter. Then you think, okay, where is it most likely that I might have made an assumption or a measurement that might not actually be true? The one that I made a mistake in was when I measured the diameter of the equipment I'm going to use to poke the hole, right? I assumed that when I poke that hole, the diameter of the hole will actually be equal to that. Well, this is actually a styrofoam cup, right? So when you poke a hole, a lot of times the hole closes back in, and the effective diameter of the hole is not actually the same as that diameter. So what I'm going to do is cut open my cup. Okay, now I'm going to measure this diameter. So it's actually not 3 millimeters at all. A lot of it closed back in. It's around 1.8 millimeters. Do we have to go back and change lots of things? I don't think so. The only place that I used the diameter of the hole was really here, right? It doesn't change the equation for the x. It doesn't change anything. Basically, we go in and change 0.00. The new diameter is going to be 1.8 millimeters or something close to that, right? Then we're going to take this and change it. Instead of 003, it's going to be 0018, right? To the power of 4. Then over here, 0.0018 to the power of 4. And then this number is going to be most likely bigger, right? Is much bigger. We're likely to get an answer that is more closer to what we actually ran. Okay, so we go back to the integral, and all we do is just change that slight number. We get 300 seconds, pretty much, 301 seconds, right? Much difference, right? Before we got 108 seconds. This time we get t is equal to 301 seconds. So basically that is t is equal to, divide that by 65 minutes, right? Actually it works. We got 4 minutes 40 seconds, right? So if you measure the exact diameter and the exact top diameter, bottom diameter, the exact height, make sure you don't make any mistake. You can actually get an answer that is even closer to the experimental answer, and it works out pretty good, okay? So actually now you can see an example of drainage problem where the diameter of the water level is changing as the water drains. So there's lots and lots of calculations, lots of good integrals. This is a pretty good problem, okay? I hope this helps you to see how to approach these kinds of problems. Thank you very much.